Already? Okay, so the title of this first talk is slightly different than what's on your schedule. This came about because of conversations with John Finnegan and Happy and the desire to have several team projects that do not require enormous amount of background knowledge about the specifics of the topic. So with this, we decided that perhaps the first lecture could be almost a math review of some of the tools that will be needed in the next lectures. And I have tried to prepare a lecture along those lines. And so the title of this lecture is the theoretical minimum. The title is stolen from an exam that is given by the famous physicist Lev Landau. And Landau, who's a great Russian physicist, used to give his students an exam, basically, to assess whether it's worth for him to spend time working with them or not. And he used to call the exam the theoretical minimum. And that exam was a 13-part exam, by the way, so it was not a light one. And basically, that exam covers everything that Lev Landau knows. So basically, to work with Lev Landau, you had to know as much as Lev Landau about physics. And apparently, something like 20 students passed that exam over the entire history of Russian physics. Now, this is not what we want to achieve here. We are actually closer to a second level of theoretical minimum that was suggested by Leonard Susskind, who's a professor at Stanford University, also theoretical physics. But in fact, what Leonard Susskind decided to do is to offer some tools and some background about physics for researchers who want to move into physics. And that basically cut down on Landau's list from something like 13 to something like 6 items that now you need to know about to do physics. The theoretical minimum here, as articulated by John Finnegan, is that, hey, look, if you like nature and you like to study it from some perspective of mathematical tools, you're in the right place. Okay, so that's our theoretical minimum. But just to make sure, we're going to cover some few points on that. Okay, so before I start, let me introduce the speakers. We are fortunate to have a group of speakers from outside and inside the KIT. The cluster of speakers that you see from outside KIT include John Finnegan from the Commonwealth Science and Industrial Research Organization, and more recently from the Australian National University. John has probably worked for the last 15 years or so now, almost, 10, 15 years on complex system science. He's been leading, actually, the Complex System Science Initiative in Australia and has saw enormous amounts of projects and topics that have dealt with complex systems. And he was kind enough to agree to give an extra lecture instead of my seed dispersal lecture on topics that are pertinent to complex system science, population dynamics, collapses, and so forth. As you will see, social systems share a lot with turbulence, and that's already an interesting phenomena about flows. So John also is perhaps more known to many of us on his work in fluid mechanics and canopy turbulence. In fact, micrometeorology as a field was born from plant science for obvious reasons. The microclimate does affect plant productivity. And for those of you who have studied some basic atmospheric science and have read the paper by Monin and Nabokov, the famous paper that has laid out almost the foundations of micrometeorology, the paper actually starts by talking about the substrate on the land surface, carbon, temperature, everything. And in fact, many of the physicists that were working at the Russian Institute where Monin and Nabokov worked later bifurcated to other topics, but they all started working on turbulence. And my colleague Amilcare Porporato from Duke University summed it up well. He said, if you work on turbulence, you are really training well for everything else. So that was kind of his statement. And that's why he has all his students take some of the most serious turbulence courses. John's contribution basically was to take a field that had a lot of empirical results in terms of transport processes near the canopy-atmosphere interface and transform it into a field that is now basically contributing to fundamental understanding of physics of transport phenomena next to interfaces. And I think this is one of the areas where environmental sciences actually is now in a position, thanks to people like John and Mike Ropak, to actually contribute to physics of turbulence rather than the other way around. Kari Jensen, who will be arriving later in the course, is a professor at the Technical University of Denmark. Kari actually finished his PhD quite recently, I think in 2010. And since then, he has been doing probably one of the most innovative and leading work, both experimental and theoretical, on water movement in plants, microfluidics, how water moves in the xylem, how water moves in the phloem, how all this network operates, how plants respond to pressures based on very innovative ideas that are coming from theoretical physics. And just to show you that our field now can be labeled truly as physics, that would be the sign if you're able to publish a paper in Reviews of Modern Physics. So, and that's what Kari Jensen just did. So in 2016, he had a very nice review paper on water movement in the xylem and the phloem in Reviews of Modern Physics. So now we are officially in the physics realms of our research. And certainly Kari is spearheading a lot of that effort. But by the way, also, if you look at Kari's CV, this guy can publish easily in Plant, Cell, and Environment, New Phytologist, Physical Review Letters. The Physical Review is actually where Albert Einstein got his first introduction to the peer review process, if you're wondering. Science, Nature, Proceedings of the National Academy, with great ease. I think when he finishes a paper, he debates, should it go to an ecology literature or should it go to probably a physics literature. So very, very sharp guy. Now, Wilfried Conrad, on the other hand, who is here, had a very interesting trajectory to get to the point where he is. He started actually, also he finished his PhD in theoretical physics. His PhD work was on deriving basically analytical solutions to Einstein's field equations. But then discovered that if you derived an analytical solution for Einstein's field equations, there is nothing else to be done. So he had to change. And at that point, he decided that if he's going to change, he's going to work on a topic where the equations for the problem have not yet been derived. So he connected with Anita Roth. And with Anita, he basically discovered that there's a whole field in ecology that is still struggling to even come up with the basic equations to describe the mechanisms in it. And I have to say that Wilfried has done a fabulous job at spearheading a lot of the initiatives that try to understand why plants look like that. Can we learn about the past climate from the shape and the function of what we think plants have done or are doing now? So basically, Wilfried's research connects quite a bit to climate reconstruction, but from a physiology perspective. And because of his background, it's always fun to chat with Wilfried. He will find something different even if you give him a quadratic equation. He will give you an insight that you did not think about when you walk to talk to him about that. Costantino Manis is a professor at Polytechnic of Turin in Italy. Costantino, or Costa, has done his PhD actually in Aberdeen in experimental hydraulics with Vladimir Nikora, one of the best labs actually to do experimental hydraulics. And he focused quite a bit on a similar problem to John Finnegan's, but rather than look at plants, he was looking at gravel beds. And in fact, if you talk to hydrologists, a major question is what's happening in the hypereic zone between streams and the land surface. And that actually is where a lot of biogeochemistry happens, temperature gradients happen, and in fact, a lot of life is impacted by that zone. So Constantin has been working extensively on figuring out the connection between a free-moving fluid and what is happening inside the gravel bed. And he later extended his work to focus on basically how live fish and so forth capitalize on the exchange processes within the hypereic zone to enhance their chances of survival and so forth. So he's going to be giving 2 lectures as well on this topic. Stefano Manzoni is one of our own from Duke University. What can we tell you about Stefano? He finished his PhD, and the day he defended, he had a paper in Science. So and it was about decomposition of leaves or something like this. I don't remember. But basically, Stefano has studied with Amilcare Porporato, who is perhaps one of the leading experts on ecohydrology. And what Stefano has brought to the table is innovative tools about stochastic processes, dynamical systems theory, physiology, hydrology, and he's able to merge them all together to attack some of the toughest problems in the field. And he's been recently moving more and more towards the use of stoichiometry as a constraint on flows. So basically, how would dimensionless numbers that are set by stoichiometry basically constrain the entire biogeochemical cycle budgets in landscapes as big as the planet or as small as the root zone. So this is a snapshot of the external speakers. Now we can go to our own from KIT. We'll start with Matthias Moder. Matthias finished his PhD with Thomas Fouken, and just like Lev Landau has the theoretical minimum, if you want to work with Thomas Fouken, you better study the energy balance closure problem, okay? There is just no way around it. You have to do something there. That's the theoretical minimum of Thomas Fouken. But Matthias was able to do way more, okay? And he was able to basically set the stage for a lot of the data processing machinery that is now being used in FluxNet, thanks to his effort. And then he decided that he had enough of this, so he went to Canada, did a postdoc, came back, and it is safe to state that Matthias is probably now one of the leading experts on computational methods on flows on complex terrain where the biosphere and the atmosphere are talking to each other or intersecting. And unlike some of the work that we have done cheapishly with flat surfaces, and so forth, actually Matthias is dealing with real systems. And both, he's bringing innovative measurements as well as simulation tools to these problems, and basically in the last 5 or 6 years, the simulations that are coming out of Matthias's group are just pretty impressive. I mean, it was unbelievable in terms of what is being done now. Okay, moving to Nadine. Oh, Nadine, I'm sorry, I forgot the 2 dots. Where is Nadine? Yeah, Nadine actually finished her PhD with Nina Buchnan from Switzerland. Nina is probably one of the top-notch grassland ecologists, I would say. It's safe to say that, and cropland ecology, actually. And she did a lot of work on carbon stocks, carbon fluxes, then went to one of the better-kept secrets in US academia, Oregon State University, where she worked with Bev Law and many others in that group, and continued work on how climatic perturbations impact water and carbon fluxes in the soil plant system. And Nadine, very much in line with Matthias, is bringing innovative measurement techniques. She is actually heading the greenhouse that you see when you enter KIT. All the experiments that you see there, all these high-tech experiments are actually Nadine Roer's. But at the same time, Nadine has several papers where she is using innovative models to also understand the coupling between radiation, microclimate, soil processes, and plant responses to them. And she has delineated an area at KIT which is looking at physiological stress, basically how elevated temperature or reduced soil moisture content impairs plant operation. We're leaving the best for last. No, it's just alphabetical order. Hans-Peter Schmidt, and Happy has mentioned our meeting at the FluxNet, but he didn't mention a couple of other things that I'm going to fill the gaps for. When we met Happy, there was on a table discussion about how to interpret fluxes, and Dave Hollinger, among others, was suggesting that maybe we should be using footprint models, and went to proceed to describe what the footprint model is to a more general audience and Department of Energy managers who were at that meeting. And then this guy from the room that nobody has seen before asks a question about the footprint models. And it was a very deep question, and we were looking at this guy saying, well, who is this? And then Dave Hollinger says, and who are you? And perhaps Dave Hollinger did not link the two, that the model he was presenting is actually Hans-Peter Schmidt's model. And Happy was the person asking him about his model. So that's how we got to know Happy in the first meeting of the Department of Energy. But of course, footprint models now are widely in use. At that time, that was not the case. And the idea of connecting what was on the land surface with what you typically measure in the atmosphere was an open problem, but it was definitely needed because flux towers were proliferating everywhere, and being able to link them to what actually the sensor sees on the land surface was an open problem. But Happy already had the solution, so it was just, he was always ahead of everybody else. And by the time we appreciated the solution, everybody was talking about aggregation and integration and so forth. But by then, Happy already had papers on that. So, you know, you get the trend. So this is the group of speakers that are going to be offering lectures. I cannot say that when I was a graduate student, I had the opportunity to interact with this prolific group of speakers. So certainly take advantage of it. Any questions about the speakers? Okay. Okay, so now we are back to the theoretical minimum and the lecture. And so thinking about projects for group effort, we thought that it might be important to have at least several topics that do not require high technical skills about the science of the topic. But perhaps if we can frame these problems in more general settings that require some mathematical skills, but at the same time, not technical skills about the specifics of the problem, then perhaps one might argue that sustainability research is probably a good one to start with. And perhaps a major question confronting sustainability research today is to what extent our planet, with a finite environmental resource base, can accommodate the faster than exponentially growing population. And this is, of course, a question that is on everybody's mind. Report after report from the United Nations are attempting to understand whether the planet can handle the faster than exponential growing population. So you are now wondering what are the connections between what we're going to talk about and this problem. They will become apparent, so be patient. Now, these concerns are often attributed to Reverend Thomas Robert Malthus. His famous essay on the principle of population basically suggested that if the population is growing exponentially, but the food supply is growing linearly, there is a problem. Okay? And that problem is basically attributed to him. But by no means he was the first to appreciate this problem. In fact, the Dutch were ahead of the Brits on this one. Early attempts to estimate how much the carrying capacity of the planet is were done by a very famous Dutch microbiologist by the name of Van Leeuwenhoek. I hope I'm pronouncing his name correctly. Now, Van Leeuwenhoek is attributed to perhaps creating the field of microbiology and using microscopes to study, actually, microbes. So he was among the first to do that. He's also famous for being friends with Vermeer, the famous Dutch painter. So, you know. But on his own, in terms of accomplishments, in 2004, the Dutch population was surveyed about who they think is the most influential Dutch person, so to speak. And Van Leeuwenhoek ranked number 4, ahead of Johan Cruyff, for those of you who know who Johan Cruyff is. Okay? Which is speaking a lot about the Dutch, okay? That they actually value the scientist over a football player. So anyway. Now, Van Leeuwenhoek, we will describe now what he did, came up with an estimate that the carrying capacity of the planet, that was in 1632 or just in the 1600s, came up with an estimate that the planet can handle 13 billion people at that time. Okay. Now, you may wonder how he did that. The crafty devil. Huh? This is what he did. He said that if we assume that the inhabited part of the Earth is as densely populated as the Netherlands, Holland at the time, which had about 1 million people. And of course, if we're managing the land on the planet as efficiently as the Dutch, okay, and since the Netherlands was 13,000 times smaller than the inhabitable land mass, he estimated that the planet can handle 13 billion people. As simple as that. Okay? So where does that estimate sit relative to the most modern estimates that we have from the United Nations in terms of projections? Well, here's one. This is the most recent. I literally downloaded this graph maybe 2 weeks ago. And it shows on the x-axis time, and on the y-axis the population in billion. And it shows roughly the trends from 1950 to 2000 and roughly 16. And then it offers a bunch of projections, and these projections, have some prediction interval uncertainties depending on what you assume as an intrinsic growth rate. And you can see that the projections are beginning to saturate or flatten at about, maybe 11 billion or so. And I've put for reference the prediction by Van Leeuwenhoek in red line at the top. Now, to go back to Malthus, so we don't leave the guy alone. Now, Malthus actually predicted that the world population would add 1 billion every 25 years. If we analyze the record that was published by the United Nations, you find that, in fact, we are adding 2 billion people every 25 years. So certainly double of what Malthus has predicted. Interesting. So how is the carrying capacity determined in general, either through projections and so forth? Well, the workhorse model actually comes from the work of Pierre-François Verhulst. And in it, this is probably known to everyone, but it's worth putting on the board. In it, he argues that the population can be exponential, but that exponential at some point faces some limitations that are density dependent. And so you could see, basically, that the density dependent correction is here, the exponential growth is here, and the outcome of this analysis is that you get a population that saturates at some carrying capacity k. Now, you could write this equation a little bit differently, and there are many forms of it in the literature, but you know, one form is shown here, where you have a proportionality constant multiplied by the population multiplied by the carrying capacity minus the population. And when you see a differential equation, it's always interesting to ask the obvious question, what's going to happen if I wait for a very, 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 very long time? Okay. So what happens typically if you wait for a very long time? Well, you are likely to reach steady state or equilibrium. Okay, so you could say that, fine, you know, the obvious point to start studying differential equations is the equilibrium points. And these are typically viewed as special cases of steady state. Thermodynamically, they are special cases of steady states, even though in the dynamical systems literature, the usage of steady state and equilibrium is a little bit loose. But from a thermodynamic perspective, there is a difference, you know, and we can discuss that if you're interested in the difference. A system that is in equilibrium must be in steady state, but the opposite is not true. A system that is in steady state need not be in equilibrium. Okay. So I'll leave it up to you to see how we might figure out which is which if I give you some information. Of course, at equilibrium, the rate of change goes to 0, and suddenly, rather than studying a differential equation, now you're studying the properties of an algebraic equation. Well, that is easier. Okay, and basically what happens at equilibrium is that you get the rate going to 0, and you get two possible solutions that satisfy this algebraic equation. One of them is the population going to 0. Yeah, if I multiply, if p goes to 0, this quantity all becomes 0. Or if p goes to k, also it makes this derivative 0. Right? Okay, fine. So fine. We found the equilibrium points. Now what? Well, the next thing you do in any theoretical analysis is you try to assess whether these equilibria are stable or unstable. Meaning that if you reach this equilibrium point and you kick the system a little bit around this equilibrium point, what happens? Do I go back to equilibrium or do I jump to another state? So to do that, we have to figure out ways to assess the stability of equilibrium. And this is all preparation for John Finnegan's talk, okay? I think. So as we shall see in a minute, that extinction in the logistic equation turns out to be an unstable equilibrium. So the minute you create population somehow, then you're going to propagate all the way up to the carrying capacity. The carrying capacity turns out to be a stable equilibrium. And the way you typically assess that is by what is called linear stability analysis. And the way you do this is you basically start with the dynamical system, in this case, the population. And you equate it to 0, and you evaluate the equilibrium points. Then what you do is you introduce a small perturbations from equilibrium. So in this case, delta is some small perturbation around the equilibrium point, p star. In the case of the logistic equation, p star was either extinction or the carrying capacity. So it's very two values. Then what you do next in this analysis is you expand this f of p around the equilibrium point, and you butcher all the higher order terms in the Taylor series expansion. So you are left with the first order Taylor series expansion of f of p around the equilibrium point, f of p star. And if you do that, you find that the second correction from p star is ddp of this function evaluated at the equilibrium multiplied by the perturbation. So far, so good? Okay. So we have just neglected the higher order terms, and that has an important implication. Basically, we are assuming that this derivative at equilibrium is finite. This could be a problem, okay, that will put a monkey wrench in linear stability analysis. But let's proceed. Let's assume that it is finite, okay? So let's now shift a little bit from the logistic equation and keep the discussion in the most general sense. So let's assume that x is our state variable, and f of x represents the derivative of x with respect to time, and we have found the equilibrium x star. So basically now we perturb x star by delta, and if you differentiate basically dx dt, you find that it is d delta dt plus dx star dt, and of course dx star dt is 0 at equilibrium, and that has to be the Taylor series expansion of f of x. So that would be f of x star plus the derivative of x with respect to x, evaluated x star multiplied by the perturbation multiplied by all the higher order terms, and that has to be 0. Now, because we are at equilibrium, f of x star is 0, and dx star dt is by definition 0. That's how we evaluated the equilibrium. So we get rid of those, we get rid of this, and we are left with d delta dt is now the derivative of x evaluated at x star multiplied by delta. So this is a first order differential equation that describes how the perturbation will grow in time. Yeah? And the direction of that growth is going to be dependent on what this derivative will do at equilibrium. Okay? So if it is 0, you have a problem. Okay? Linear stability analysis is going to choke a little bit. There are ways around it, but it will choke. If it is negative, then you have something that looks like d delta dt is minus some number multiplied by delta, and the solution of this is a negative exponential in time. So you know that the perturbations are going to decay in time, and so we can call the equilibrium stable, because whatever we do, if we perturb it a little bit, it's going to relax back to this equilibrium. On the other hand, if f prime of x star is positive, something else happens. Now, if we perturb the system, in fact, these perturbations grow, and very soon they will stop abiding by linear stability analysis. Okay? But we know one thing, that these perturbations are going to move us away from this equilibrium point. We're not going to relax back to this equilibrium point. Again, this whole analysis is making the assumption that the derivative of f of x, this generic function that describes the derivative of x with respect to time, is finite at equilibrium. Okay? So let's now specialize again into our logistic equation and see if we can recover the intuitive results that we know about it, that basically extinction is unstable, carrying capacity is stable. If we evaluate the derivative of f of p that is given here with respect to p, we find that this derivative is alpha multiplied by k minus 2p. So if we insert the extinction equilibrium, we get alpha k to be positive, so that's clearly unstable, right? Because if p goes to 0, we are left with alpha k, and that's a positive derivative. Whereas if we go to population reaching carrying capacity, we have k minus 2k, so we get a negative number here, and that equilibrium is unstable. Okay, stable, sorry, because the derivative is negative. Okay, so basically we just showed that this is the case. Fine. There is one more thing that you could learn about this analysis, which is a relaxation timescale to equilibrium. Okay? And that's another important concept. Relaxation timescale, basically, you could show very quickly that 1 over the derivative of p evaluated at equilibrium does describe, as you might expect, the timescale at which you decay or you move away from equilibrium. And again, in the logistic equation, if you plot the value of f prime of p star at the equilibrium, the carrying capacity, you find that you would relax to equilibrium at a rate of 1 over r. But in general, in any dynamical system, you could think of f prime of p star, where p star is the equilibrium point, as almost a relaxation timescale. Okay. Now we come to the discussion about basically what is going to happen to the population in the future. Now, the United Nations analysis has taken a short-term view of about 50 years or so to understand or project what will happen to the population in the future, and perhaps use the data from 1950 to 2016 or so to try to estimate the carrying capacity of the planet, depending on different growth projections. But if you take a much longer viewpoint, of human population, and that is shown on the graph here, where the y-axis is the world population, the x-axis is year. Now we have, so to speak, the ability to reconstruct world population starting from almost 1 AD, yeah, roughly. And if you look at the human population since that period of time up to today, it looks that it is growing faster than exponential, which brings the sustainability question that we started this lecture with into focus. This is exactly what we mean. How can we explain the faster than exponential growth in human population if we are anticipating to see carrying capacity restrictions kicking in? This point was not missed by the famous physicist Heinz von Foerester, and he had a wonderful paper in 1960 where he actually brought this point up. He said, hey, there is something fishy. If you have faster than exponential growth in human population, that cannot be compatible with the logistic equation. The fastest growth you could see in the logistic equation is exponential. So if something is growing faster than exponential, it means that the whole assumption of your logistic equation and any projections from it comes into question. Right? Okay. Now, the paper was quite catchy, very stylish, also very well written and very humorous if you read it. And I'll explain a little bit the humor as we go along. He titled, this was Science, yeah? This is when the days where, you know, you could publish a paper in Science and have a little bit of fun and still do serious work. Okay. So the paper was titled Doomsday. Friday, the 13th November, AD 2026. At this date, human population will approach infinity if it grows as it had grown in the last 2 millennia. Now, the crafty devil, this guy, Heinz von Foerester, I mean, with few data points, he was able to do miracles. It's a little bit like Wilfred Conrad in that sense. You give him few data points, he could do a lot. And incidentally, the co-authors with Heinz von Foerester happened to be 2 undergraduate students who were taking his class. So just... Okay, so he actually decided that, you know what, to really try to understand the limitations of the logistic equation, there are 2 ways to look at it, you know, as in life. Yeah? You could be an optimist, or you could be a pessimist. So he was trying to interpret what it means if the population is growing faster than exponential, which is pretty much what the people in stable isotopes do, yeah? They look at the 2 end members and they come up with a mixing model. So his argument is that we can identify the 2 end members, then we can figure out everything in between, yeah? So he pitted the pessimist against the optimist, basically, in this paper. And he said, if you're a pessimist, you'd say, hey, sooner or later, the carrying capacity is going to kick in, environmental degradation is happening, you know, we're going to be able to sustain less and less, and still, at steady state, we're going to reach a carrying capacity pretty fast that is going to depreciate, even though we don't see it now in the human population. But it is looming in the background. So that was his pessimist view. He actually, you know, made it sound like this view is so boring that it's not even worth exploring beyond what I have just said. Okay? The more interesting one, according to him, is the optimist. What is the optimist? The optimist basically will make the claim that the carrying capacity can increase with population due to technological innovations. If you think about the problems now on the planet, you could distill them pretty much to water, food, energy, and disease. I mean, you know, we all know what the big problems are. Okay, I think it's safe to say that they are pretty much decided upon. Okay, and we all know that they are interlinked. They are not entirely independent problems. Okay? The challenge is how do you draw the boundaries around the inquiry of these connections. But I think it is safe to state that we are well aware of what the big problems facing humanity are. Okay? And so he said that if you're an optimist, you could say, well, every time we have had carrying capacity limitations kicking in, we have seemed to have found a technological solution to overcome it. So that's the optimistic view. So if it was food limitations, we found agriculture, we found fertilizers. If it is quote-unquote health, we found vaccines, we found antibiotics. Energy, we have fossil fuel, we have fire, you name it. So it seems that every time we hit a bottleneck, the population as a whole was able to find a technological innovation and eliminate that bottleneck. So that's the optimist. Well, which is pretty much what you would see now in most political debates. No, it's more or less, you could distill it to these 2 simplified views. So then let's explore what happens if we pursue the line of arguments of the optimist. Where does that take us? And that's what von Foerester just did. He said that, okay, well, if this is the case, then a macroscopic description, so we're not really concerned about a society in this area or that area or whatever. We're looking at the whole globe. Collectively, our collective knowledge, how it gets transferred, how we do things, it is not really the issue here. But collectively, we have seen that the carrying capacity limitations have been overcome because of the population growing. So the more people we have, according to the optimist, the more probability we have to find a technological fix to our limiting carrying capacity case. Okay, so fair enough, that's a very optimistic view. So he said, well, if you are really, really optimistic, then the carrying capacity will scale with the population, raised to some power. And that power would be bigger than 1. So that was the most optimistic you could get, according to him. You cannot get better than this, okay? So where does that take us? So he decided to go back and revisit the logistic equation. So he said, if you go back to the logistic equation with this model of the carrying capacity that is now not constant, but grows, yeah, with human population, because you're able to find all these technological fixes. It grows with the human population. Then the logistic equation reduces to this form. We have dp dt, rather than being a constant proportional to the carrying capacity here, it's actually dependent on the population raised to some exponent, delta plus 1, minus the term that is actually causing the reduction in population, p squared. Now he said if delta is bigger than 1, so this exponent here is bigger than 1, and as the population increases, this term that is here, this term that is here, will dominate the solution, because this term is, say, cubical, or 4th power, or 5th power. This term is reducing the population as quadratic. For sure, for big populations, the bigger the power, the more dominant that term is going to be. Okay, fair enough. So let's do some simplifications. We're going to get rid of this term and just leave the big term, okay, when we're looking at the difference between these two terms. So he did that. And basically, you could simplify that for large populations. The logistic equation now looks more like that. dp dt, the rate of change of the population with respect to time, scales with the population raised to some delta plus 1. And even I can solve this differential equation. So if you do that, you find that the solution turns out to be the exponent itself, delta, multiplied by this proportionality constant r prime times t minus some integration constant raised to the minus 1 over delta, which we can write a little bit this way. Okay, so now we have something here that looks like time in the denominator. Fine, let's try to get rid of this integration constant by imposing some plausible condition. Say we know the population at some time t equal to 0, say 1 AD, yeah? So let's assume that P of 0 is P0, so that could be a reference point that you pick, but not the Garden of Eden, okay? Because that would be small populations. Okay? So P of t then becomes, when you impose this initial condition, and now you have P0 as the initial population, it becomes actually shown here. And automatically you see what's going to happen now with the optimistic solution. There is a chance that if t goes to P0 raised to the minus delta divided by delta r, the denominator of this quantity will go to 0, raised to some positive exponent, and 1 over 0 is infinity. Interesting. So at finite times, we can have an explosion in population. This is known as finite time singularities. Okay. The concept is not new. If you talk to engineers, they've already knew about critical time to failure. But it was an interesting idea in terms of population dynamics, that the population, in fact, as von Foerester hinted at in the title of the paper of science, that this is in fact an explosion in finite time of population. Now, what does that really mean when we say population goes to infinity? Well, the universe cannot handle that, no? What's happening? Well, this is a little bit of an interesting discussion. You actually never reach the critical time, right? What happens is that the system crashes and new dynamics have to emerge, okay? So the history of the population dynamics that was describing the time evolution of the population after TC will no longer hold. Okay, it's a little bit like the Big Bang. Yeah, if you think about the Big Bang, you could say, hey, the universe started 13.6 billion years ago. What was there before? Who knows? There was no time. Time was created after the Big Bang. Okay. There was no space, okay? So the whole question is wrong, you know. So what was before the Big Bang? You cannot ask that question. There was no time, okay? Similarly, after the critical time, the dynamics of that population are no longer described by this differential equation. Does that make sense? Okay. So it appears, therefore, that, yes, when you reach this finite time singularity or this critical time, the dynamics have to change, basically. And new dynamics or new regime change, to borrow from our US politicians when they want to change regimes in countries, yeah? Same idea, but that is external rather than endogenous. Okay. So now, what did von Foerester calculate based on what he knew out of curiosity? He used the data set, fitted the data set to his power law model, and estimated that the critical time would have been 2026. So that's a calculation. Okay. Now you could say, okay, we understand the 2026, but what about this 13 November? Where did that come from? I mean, certainly the population dynamics was not that precise. Now I can only offer a conjecture. Okay. Von Foerester was born on November 13th, 1911. Okay. And if you do the calculations, it turns out that November 13th, 2026 would have been his birthday. So it gives you a sense of the style of the paper. Okay. He snuck it in science. You have to give him credit for that. Okay. So with that, there are still a few questions that were pretty entertaining that was asked by von Foerester. Didn't stop here. Didn't stop here. There's more to come. Okay. But just to summarize the outcome, he says, hey, look, if you are an optimist or a pessimist, if you are a pessimist, you are Malthusian by profession. Yeah. Your job is to be negative. If you're an optimist, you are Malthusian by heart. Okay. That was the conclusion of the paper. But there is actually more. So he said, hey, as much as it is fun to use mathematical models to predict the future, it's equally fun to try to go back in the past. And he actually asked an interesting question. He said, if we use the Doomsday equation to go back all the way to the Garden of Eden, how long would it take us? Okay, how long would it take us to go back to a population of 2? Time reversal. Okay, clever guy. Okay, so he didn't miss this point. He did not miss it. Okay. So he used the original Doomsday equation and reversed time and said, okay, well, what would be the time to reach 2, Adam and Eve, say, you know? And it turns out that you would need more than 20 billion years. Now, if the age of the universe is 13.6 billion years, we don't know what's happening between 13.6 and the creation of the Garden of Eden. But the question is why? And he actually had a very good answer. Nothing misses him. Okay. This is all coming from some 20 data points about the human population. Okay, just to show you what 20 data points can do in the hands of Heinz von Foerester. I'm sure even Wilfred will agree this is impressive. So he actually says, well, you know, to actually reach a phase where the carrying capacity depends on the population, you need at least a population base, because you need information storage. You need actually the population to grow to a sufficient size before you could invest in scientists, in research. You need to store food. You need to be able to have a certain infrastructure in place before the carrying capacity actually grows as a function of the power law of the population. As a project, there are 2 interesting things that we could ask before we go next. First, how stable are those calculations of critical times? Okay, this is an important problem. Because basically what you are saying is that if you have a system, if you have any dynamical system that is growing as a power law with an exponent that is bigger than 1, this system will experience a crash, a finite time singularity. But how stable is the calculation of this finite time singularity? If I give you 10 points, if I give you 20 points, do I get the same answer? Or is this critical time seems to be a very moving target, yeah? So one of the things that we would like to explore together is I've put the data set of von Foerester and more recent updates up to 1998 on the web, and so we can actually play around fitting models like the one of von Foerester and see if we start adding every year from 1998, you know, or even starting from 1960, we start adding incrementally year by year information about the population, and we track how well do we reach the critical time, how stable is the critical time, okay? Is it a moving target? Every time we add a little bit of data points, the critical time also shifts. Becomes almost like chasing ghosts. Okay, so we're going to do a little bit of that. But we're going to do this not just using von Foerester's equation, but also some other approaches. Now, the topic of von Foerester was picked up by another physicist by the name of Didier Sornette. And Didier Sornette has worked with the European Space Agency for a while and was looking at material failure, okay, because they didn't want a repeat of NASA's explosion in 1986. So basically, Didier Sornette has looked at material failure for a while and noticed that material failure, especially fatigue, shear crack propagation in materials, tend to grow as a power law too. But there are some interesting oscillations around it. And then when he revisited von Foerester's paper, he fitted a power law to the data set that he had, and that was up to, well, the paper was published 2001, so probably up to 1999. And he found that this critical time that von Foerester has calculated as 2020 suddenly becomes 2030. Okay, so that's a first hint that it could be a moving target. But more important for our analysis now is that the residuals around this power law are not random. Now, if you've ever taken a course in regression, and you do a regression, the first thing you check is whether the residuals are random, right? Do they pass a certain randomness test? But Sornette seems to have noticed that these residuals are clearly structured. They seem to actually be even periodic, right? If you stare at this graph for a while, you almost see some periodicities around this power law. Does that make sense? Why is that? So he was curious. He, of course, suggested that, well, there may be a more general theory then that should be able to predict the power law and the oscillations around the power law. Is this part of a more general framework that allows us to actually see something more about the system than just the power law itself? And he tried to say, okay, well, can there be a more general theory? And the answer is a qualified yes. We will actually try to fine-tune it in this summer school. Okay. So the idea that Sornette did is as follows. He said, okay, let's take the population, and that seems to scale as a power law with the critical time minus t raised to some exponent. Then he asked, what happens if this exponent is complex, meaning it has a real part and an imaginary part? Now, this did not come just out of the blues. He knew what he was looking for, okay? And I will tell you why he knew what he was looking for. But let's proceed that, yes, maybe a complex exponent is a more general description than just assuming the exponent is real, okay? He didn't say why it was complex, okay, just to be clear. He did not offer an explanation why he would choose this exponent here to be complex. But let's humor him a little bit, and we proceed with the derivation that he had and assume it complex. What would that take us? So the idea is that you take this critical time minus t raised to this power z, and you break this z into a real part and an imaginary part, the real part being beta, the imaginary part being omega, and I squared here is -1, yeah? Then what you do is you write this quantity here, yeah, as exponent of the log of that quantity. Basically, we have just used the obvious fact that if you have a number, you take its logarithm, then you exponentiate the outcome, you get back the same number, okay? 5, log 5, e to the log 5, you get back 5, okay? Then what he did is he used, of course, the well-known property of the log that log x to the a is a log x, yeah? And then he basically separated this a into its real part and its imaginary part. So you have the beta log of dc minus d and the I omega log of dc minus d. This is all in the exponent, yeah? Then you notice something else, okay, that e to the a plus b can be written as e to the a times e to the b, okay? And that's what we did in this step. So now beta log of dc minus d plus I omega log of dc minus d can be written as e to the beta log dc minus c multiplied by exponential of I omega log of dc minus d. So all I've just done here is simply use the property that e to the a plus b is e to the a times e to the b, okay? And then what he did is he brought the beta up here, so that's this part, and he used the well-known formula that e to the I theta is cosine theta plus I sine theta, yeah? And that's what you have here. So far, so good? That's a quick review of complex numbers in case you forgot them, okay? That's why I decided to put the steps rather than just show you quickly the result, okay? So, of course, we are seeing the population in real time, so we don't see the imaginary part, we just see only the real part. So we take the projection of this solution on the real axis, and basically you get rid of the I sine omega t, but the cosine omega of log dc minus t will survive. So in this case, if you have a population that is growing as a power law with an exponent z that is complex, the solution still has a power law component, but it will be multiplied, yeah, by the cosine of omega log of dc minus t. And that is what is generating the log periodic oscillations around that power law, according to Sornette. So far, so good? Are you falling asleep, or this is exciting enough? Okay. Okay, so with this, out of curiosity, I plotted some graphs to show you that, yes, you know, the power law, of course, dominates a big chunk of the time series when you plot population as a function of time. But when you plot the population on the log axis and tc minus t on the log axis, you already see these bumps, yeah, that are coming from the log periodic oscillations. One of the fun projects would be is actually to go back and see, did they occur during certain periods of time when there was climate change, the plague, whatever, you know? Do these oscillations make sense? The fit is not bad, okay? I've checked it, actually. So one of the project ideas that we could explore together is whether if we use Johansen and Sornette's log periodic equations, we can also calculate the critical time. So is this extra information about log periodic oscillations improving the fit, stabilizing a little bit the calculation of this critical time or not? Okay, so that's one thing. We are adding more parameters, of course, so there is a penalty to pay by having more tunable knobs, yeah, but maybe the TC that comes out of these calculations is more stable, okay? So that's one of the projects, and I put some MATLAB script that does some nonlinear fitting. So in case you would like to pursue this, there is already some data set and some machinery to start the calculations. Another question that would be interesting to ask from Johansen and Sornette that they missed about von Foerester's paper is what happens when we go backwards in time? You know, what do we calculate when we have log periodic oscillations? It'll be also interesting to repeat von Foerester's calculations without the assumption of large population. What do we get out of that? Okay? So these are some ideas that would be an acceptable project, okay? Especially if you want to practice your skills in fitting data analysis and models and looking at residuals. Okay, so that's why I've put also this, in case you are looking for some ideas you want to experiment with, the data is there, okay? Now, to summarize the main point of the analysis of Sornette's paper is that complex exponents do generate log periodic oscillations around the power law, and they tend to intensify in amplitude and frequency as this critical time is approached. And that's kind of the message from Sornette's paper. And in fact, he repeated this message, almost the same message, in about Avogadro's number of papers later. Perhaps the one that is common is from the Proceedings of the National Academy of Sciences. At that time, PNAS had a whole special issue about what they call the signs of disasters, basically. And from Sornette's paper, I have a couple of graphs. One of them shows, for example, the energy release as a function of time during material rupture. So if you load a system and you keep loading it until time to failure, you see that the energy that is being released is actually spiking like that, and it almost looks like it's a regular interval. And you could almost see some power law beginning to form. Similarly, stock market crashes, yeah, you have typical almost power law rise followed by crash. And the question is that, can these log periodic oscillations around those power laws be good way to fingerprint, perhaps, collapses in complex systems? And hence, the estimation of this critical time is telling you how much lead time do you have to make a decision to reverse the dynamics or do something different before the system crashes. Okay? So that's part of the analysis that we can do with the human population. But there are many, many things that one can do, especially any system that seems to be exhibiting very rapid rise, faster than exponential, with some oscillations around it, may actually be amenable to the general treatment that Sornette has proposed. And that was the message of this proceedings of the National Academy paper. Okay, one more thing, because we're going to talk a lot about coherent structures, and I would like to also show you that this type of insights also allows you to understand something about fluid mechanics. Okay, so this is nothing but what is called the vorticity equation in fluid mechanics. The vorticity is the curl of the velocity, but it is a useful quantity to look at. It is actually often used as a measure of coherency. If a vortex is coherent, it has a big vorticity. And basically, the vorticity equation has a time rate of change that is local. There is an advective time rate of change. There is an interaction between the vorticity and the velocity gradient, and then there is a viscous diffusion of vorticity, where nu here is the viscosity. This is internal friction in the case of fluids. Now, typically, these two terms are combined together in fluid mechanics to what is called still a local rate of change, an advective rate of change that is known sometimes as the material derivative or the substantial derivative or the total derivative. This term is the viscous diffusion. We're not going to tinker with it. And this term looks like an interesting term. It's a new term that arises from manipulating the Navier-Stokes equations in a way to get rid of the pressure. Notice that there is no pressure in this equation. Okay, so if you are a little bit aware of Navier-Stokes, one of the advantages of vorticity methods is that you bypass the need to compute pressures. And pressures are more tricky because there's, hey, if you go to the bathroom and you open the door very quickly, then the water in the toilet will oscillate. Okay, it's that non-local. Okay, and in fact, in turbulence, this is the term that is responsible to vortex stretching. Okay, but we have been able to eliminate from the Navier-Stokes equations by writing the vorticity equation of it the pressure term. So why am I saying all of this, especially in connections to finite time singularities? It's coming. Here it is. In the limit of zero viscosity, so you have a frictionless fluid. Yeah? This is an interesting limit. Okay? In the limit of zero viscosity, you kick this term out. Now, if the vorticity is nothing but the curl of the velocity, then it must be proportional to the velocity gradient. So I can get rid of this velocity gradient and basically put the vorticity here. So now I have an equation that looks like dw dt is proportional to the vorticity squared. What does that say? Explosion of vorticity in finite times. Now, of course, this is much more correct in the limit of 2 dimensions rather than 3 dimensions. But the idea is there. The insights that you get from analyzing equations, now that you have some perspective about what to look for, you could see why Euler's equations, which are the inviscid equations that describe vorticity, do exhibit singularities, especially in 2D, where this connection, this term, becomes proportional to the vorticity itself. This is being debated, by the way, by the mathematicians. There's a lot of debate going on in pure math whether the Euler equations do exhibit this type of singularity. But I just want to show you, without knowing anything, without knowing anything, just basic definitions, you could reason that the vorticity equation might exhibit singularities. So that's the reason I bring this up. Okay, it's just to show you one concrete example that we're going to see similar equations in this course, that if you do a scaling analysis on them, they do exhibit some information about perhaps finite time singularities in limits of zero viscosities. And these are the good limits to try to understand. Yeah? See what happens. Okay, there is one more idea, and then I will stop barraging you with ideas on methods of analysis. There is some interesting connection, and this will come a lot in Stefano Manzoni's talk, on critical points in complex systems. Now, if you have the population that is growing as a power law, the derivative of that population can be easily computed, and you see what happens is that as t approaches Tc, not just that you have explosion of the state, but the derivative is also ill-defined. Yeah, it's going to go to infinity. And basically, that sets the stage for what we call critical points. So what are critical points or stationary points? They are points where the derivative is either 0 or ill-defined. Okay, that's a critical point. Now, often than not, you typically associate critical points with maximas and minimas because they are 0. But there is a whole slew of other possibilities for critical points. And just for an illustration, I sketched a function that looks like this. So if y varies with x and you're interested in the interval a to b, this function has, say, a local maximum, so that's a critical point. It has a local minimum, that's also a critical point. This point is interesting. It looks like the derivative there is not defined. I have a corner. Yeah? So what is the derivative there? The Italians have a word for it. Bow. And this is a critical point, okay? This is a critical point too. Not a local minimum, not a local maximum, but the derivative there is 0. And you might say, well, that is really a very boring point. Is it? Would I put it on the board if it was a boring point? I mean, honestly, what is so exciting about it? The suspense is building? Well, a new concept now. Critical slowdown. This point exhibits critical slowdown. What do we mean by critical slowdown? Remember the linear stability analysis I mentioned? What happens when the derivative goes to 0, that linear stability theory chokes or starts showing its own signs of wear and tear? Well, critical slowdown is one such idea, and we'll discuss in a minute why it's an important point for crashes of systems. But first, conceptually, what is a critical point? We show that the critical point basically is a point where the derivative is not defined or it is 0. So in this case, if you have a dynamical system where dx dt decreases as minus x cubed, surely equilibrium is at x equals 0, right? Steady state or equilibrium is at x equals 0. The derivative of minus x cubed at x equals 0 is 0 too. So already this is telling us that linear stability analysis might run into some issues. Yeah. So how do we go about determining the stability of this point? Well, the easiest is a graphical way. So what you do is you look at the dx dt when x is negative, and you find that dx dt is in fact positive, so it is heading towards the equilibrium point. You also look at dx over dt on the positive side, and so when x is positive, dx dt is negative, so it is moving again towards the equilibrium point. So it looks like things are converging to this equilibrium point. So this equilibrium point is likely to be stable. But that's not why I'm putting this on the board. Okay, this is just to show you that graphically you could figure out the outcome of stability analysis without doing linear stability theory. The reason I'm putting this point is that if you remember from our analysis about relaxation timescales, what happens when you perturb something from equilibrium and you're watching how it relaxes back to equilibrium? Now, linear stability theory, if you applied it blind, you would have predicted that the relaxation time is 1 over f prime of p star, if you remember. But this quantity in this particular system is 0. So 1 over 0 is, so it takes infinite amount of time to relax to equilibrium. That's not true. Okay, actually it turns out to be finite. If you solve this ordinary differential equation, you find that the solution x of t scales as t to the minus 1/2, and that's a very slow approach time. Yeah. So yes, you will reach equilibrium if time goes to infinity. Okay, but very slowly. So that's known as critical slowdown, because the approach to equilibrium is so slow. Okay. And there were lots of papers in magazines like Nature and Science using this whole idea of perhaps critical slowdown may be an early warning signals for critical transitions. And Martin Scheffer and many others Max Riedkirk, Stephen Carpenter, and so forth, have harped a lot on this idea that perhaps near phase transitions, you may be experiencing critical slowdown. Okay? Phase transitions, regime change, you know, you get the picture. Okay? One more idea, and this I'm going to go through this quickly, is what is called discrete scale invariance. This idea comes about that when you look at the exponent and it's complex, you find that the energy pulses in P, right, are going to come when this cosine part is maximum. And those happen to be in discrete integers of 2 pi. So that's why the pulses in the population or material failure or whatever tend to have a unique scaling. In other words, the critical time minus any arbitrary time Tn seems to scale as lambda to the minus n, where n is integers. So basically these build up and crash, build up and crash, build up and crash as the power law is approaching are quantized. Yeah, they're not everywhere. They are actually happening at quantized times, and this is why this whole analysis is called discrete scale invariance. We're not going to go through a lot of this stuff, but I should say that there is a very interesting theoretical connection to renormalized group theory and discrete scale invariance. Okay, but we're not going to touch it. It does suggest that if you have a system where you have microscopic variabilities, you could coarse grain them, come up with a macroscopic relation, and jump to the next scale and the next scale and the next scale. And you could do that indefinitely if you are guaranteed that the system exhibits discrete scale invariance. And that has been used in turbulence as well. Okay. So finally, how could complex exponents arise? In a separate paper by Edie and Sornette, this was to look at financial crashes, they proposed the dynamical model that has an acceleration term, yeah, d2x dt squared. This looks like an acceleration. And it seems to be related to a velocity that is a power law and the state that is a power law, and it's looking at the difference. And it turns out that under some conditions, this dynamical system does exhibit complex exponents and finite time singularities. So another project that, if you like to dig into this stuff a little bit deeper and capitalize on Wilfred Conrad's expertise and John Finnegan's expertise, and to build on Happe's idea that it's not just the students who should be experiencing new ideas outside the research, also the instructors. If you are interested in actually doing a formal analysis to look at how the system behaves, what happens when alpha is 0 and gamma is 0, well, that's obvious, d2x dt squared is 0. What happens if alpha is finite but gamma is 0? What happens when m is large relative to n? So there is a whole slew of possibilities to explore theoretically, yeah, about this dynamical system and see under what conditions, what ranges of m and n you would see that will give you basically log periodic oscillations and so forth. And this system does have all the necessary ingredients to do that. So if you're interested in a project that has a little bit more of a theoretical flavor, feel free to do a systematic analysis, what is called bifurcation analysis. So you try to understand what range of parameters alpha, gamma, m, and n will give you certain features of the solution. Okay, so we are almost running out of time. So the salient points to be covered that we have covered in this lecture, we've shown that power law acceleration leads to finite time singularities. This is true in population and vorticity, etc. We have shown that complex exponents can lead to log periodic oscillations that may be used to fingerprint collapses in complex systems. We have discussed relaxation timescales to equilibria. We have shown its connection to dynamical systems. We have also defined critical points, critical slowdown, and discrete scale invariance, even though we didn't discuss much of the discrete scale invariance. Okay, so this is basically what we have covered in this lecture. To conclude on a philosophical note, we use the statistician George Box, very famous statistician. Milan, he also spent some time at NC State, if you are curious. And basically what George Box says is that all models are wrong, because of course all models are simplifications of real systems. So they are wrong by definition. But he says, but some are actually useful. So that's basically a good thing to remember. Okay, so more ideas about projects. I've put 3 papers on the cloud. One of them is coming from Gabriele Manoli and Marco Marani from Duke University, as well as myself. And in it, we looked, well, actually Gabriele looked, I was cheering on the side more, about the human energy climate system. And the idea that came from there is that we stumbled on a paper way back by Didier Sornette that was looking at what is called punctuated equilibrium. What happens if you have a system that seems to be flat, 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 and that's known as a punctuated equilibrium. And it turns out that delayed differential equations, when they're applied to the logistic equation that we have just covered in great detail, exhibit exactly that pattern. So building on this idea and realizing that the emissions of anthropogenic CO2 per capita is exhibiting exactly this stairway pattern, Gabriele decided to put this idea along with a simple model for CO2 emissions and temperature, zeroth order model, yeah, of the entire climate system, and study the consequence of this type of step up and step down, yeah? So in other words, if you think of the step down as diffusion of green technology that are now dropping the consumption per capita, so you are doing this in step down, he tried to figure out what should be the diffusion time, yeah, which would dictate the step down, the diffusion time to actually meet the Paris climate agreement, yeah? So he did this and actually showed that this buildup of inertia is important, and in fact, if the step up has periods of 60 years before you see the next jump and the next jump and the next jump, the step down to reach the Paris Agreement, you would actually need to go down at a rate of 6 years. So, you know, that's how fast green technology should, at least in this model framework, should go. So if you're interested in pursuing this idea a little bit more, I've put the data set that Gabriele has assembled to run these types of models. And they're all on the cloud with the MATLAB code that repeats all the graphs in the paper, okay? So other questions that pop up, of course, what happens if you change a little bit the formulations? What happens if there is a feedback between temperature and the emission rates? You know, what happens if you add a mortality term because of warming causing more mortalities? So the opportunities of looking at a set of questions are almost infinite, yeah? But it is all there, it runs, it repeats the graphs in the paper. The model is detailed quite well, and have fun if you want to learn also about logistic equations with delays. Logistic equations with delays are worse than partial differential equations, just so that you know. So there is no way you could do anything analytical with them. Okay? The other example that I've put is the Easter Island example. This was popularized by the book of Jared Diamond, Collapse, and it's a two-equation model. And the reason I picked this example is that this is, I don't know how many of you know about the Easter Island collapse. Easter Island is a small island. It was settled way back by Polynesian settlers that had to travel thousands of miles by boat to get to it. And it's an isolated system. So this is it, you know, humans, environment, no other external agents. And of course, the population collapse. And that's a very advanced civilization that settled Easter Island, okay? And there are many, many reasons that are discussed. One of them is endogenous dynamics between the population and the natural resources. And it seems to exhibit a boom-bust cycle, okay? So that's why I'm bringing it up to your attention. It has this interesting feature about the dynamics that you have a rapid explosion in the population despite the fact that the resource is being diminished extremely fast, faster than the growth of the population. So Easter Island is there, and the paper is there, and it's very clear, by the way. It's a very well-written paper by Brander and Taylor. That's not the only reason Easter Island population collapsed. There are plenty of other counter arguments to it, but we can certainly explore some of these ideas, whether they make sense in terms of the Easter Island information that we have. The population of Easter Island was reasonably reconstructed, and the vegetation amounts were reasonably reconstructed from many other pieces of information. So we can certainly look into it. We can also try to ask other questions. What happens if there is a climate anomaly? Would that have accelerated or decelerated the dynamics of the Easter Island population? The third one is a little bit more open, but John Finnegan has already thought about that, and so that's why I'm putting it here. It's Joe Tainter has also written many papers and books about collapse of complex societies, and not just human societies, also ant societies. That's why some people actually call the outcome of Joe Tainter's work as Tainter's law. So if you Google Tainter's law, you get actually a bunch of papers. and very interesting work. He actually studied how complexity arises in in ant colonies, as well as in the Roman Empire and many, many other empires, and how this addition of complexity reaches a certain phase where adding complexity actually doesn't buy you as much return, and that would be the tipping point at which the collapse starts. And so I've put also a paper that describes this mechanism, and as a project, it would be fun to try to write a dynamical system, a very simple dynamical system that reproduces the main features of Joe Tainter's law. And John has already done some of that, but slightly more elaborate, I guess. So if we can reduce John's approach to a simpler one, we've achieved something too. And that could be a fun project as well. Okay, so with that, I stop. Any questions? So this was primarily intended to give you an overview of dynamical systems, but with a problem that I think we all appreciate and understand, that has nothing to do with turbulence or cavitation in plants, even though cavitation in plants, the spread of embolism does follow a logistic equation, very similar to what we have covered. So.